Thank you for coming to this talk. We are already 5 minutes late, I think. I'll try to keep it within time. This talk is on building a recommendation engine using Python, which is a type of predictive analytics. And before I dive more into the topic, I will tell you a little bit about me. So I am a my name is Anusua. I am data scientist at Texas Advanced Computing Center, TAC. It is an independent research center at UT Austin. It is one of the largest supercomputer center which is HIPAA compliant. We have about 250 people working in this lab, in the supercomputer lab, and we collaborate with mostly the other national labs and federal government agencies. So we work on many classified projects and very innovative and novel projects. So one example of our work would be how to better predictive analytics for the weather system so that it balances our ecosystem, things like that, and recommendation on earthquakes. These are a few examples of the kind of work that we do. We work a lot with patient data also, like predicting diseases, predicting drugs for specific diseases. So we work a lot with life sciences, like genome sequencing, those kind of data also. And being a supercomputer center, we work on large-scale computing problems. So we have several supercomputers which work on very powerful GPUs, as well as the data analytics. We have a supercomputer called Wrangler, which came out recently, and it works specifically on data analytics portion. I'll show you a little bit the interface that I have here. So this is the interface in Wrangler where you can go and you do not have to set up any cluster. You can just say, in the request new Hadoop reservation here, you can just say how many nodes you want and for how many days. It will just spin up a cluster for you so that the data scientist just needs to take care of the experiments that they do and just do not worry about setting up a cluster and things like that. So once you set up this, no, it's not, okay. You are assigned Hadoop clusters like this, and you can just go into your cluster and start working. So this is a very typical example of how we work. Now, on the motivation of my talk today, why do we need recommendation engines or recommendation systems at all? I mean, there are many packages, many libraries already existing. So why do we need another new one? Most of the cases we have seen that most of the packages that are readily available, whether it's open source or if you buy it, those packages actually take into consideration mostly numerical data. They do not take into consideration image processing, text analytics, recommendation on these kind of data, very unstructured data. So the main motivation behind this recommendation engine was to build an in-house one, which we can store in the Wrangler supercomputer, where people could come and just grab that code and run it with their own data set. So it's as Wrangler runs on Hadoop and Spark-infused platform. So PySpark can actually, if your code is in Python, PySpark can actually utilize the Hadoop HDFS system underlying, and you can process very big data sets in Wrangler. And if we put this, our hybrid recommendation model, which I'm going to talk about, there you can just come in and it can do recommendation on your own data set. So a brief outline of my talk today. I've said that recommendation systems is a type of predictive analytics. We'll just compare and see how it is. I will give you a brief introduction of recommender systems, types of recommender systems existing, recommended systems for PubMed document. As I work mostly with medical data, I've chosen PubMed document, and we'll do a hybrid model of recommender systems on PubMed documents. Going forward, this could be used on any kind of documents, any text format. If you want to work it on your own kind of data, like specifically like image data set, you can contact me and we can collaborate. I mean, we are always looking for collaborations in TAC. We can collaborate and work together on it. And I'll give you also a very brief workflow and a live demo of a small case of the system. Like I cannot show you on the supercomputer; it will just take forever. I've just show you a local live demo of how we go about doing this. Before comparing, the predictive analytics and recommended systems, I go to the data analytics, go back a step. So I go back to data analytics. And we see here that mainly 3 types of data analytics are existing here: descriptive, predictive, and prescriptive. So descriptive is the very, like the simple type of data analytics that you can do. It just gives you an aggregate view of your data and just takes the data and breaks it up into small useful chunks so that you can have a very top level view. The vast majority of the statistics that we use, like sums, averages, percentage changes, this kind of things falls under descriptive analytics. Next, which is in rage nowadays, is predictive analytics. It takes your data and tries to predict a trend in your data. It is a probabilistic prediction. It does not give you the future. It just predicts what will happen with your data in future. One kind of predictive analytics example, a very common one, is sentiment analysis. One such example would be if you're trying to find out whether your email is spam or not, you can apply sentiment analytics, and it will predict based on the sentiment of the email that whether it's a spam or not. The next type of predictive analytics, which we'll talk about today, is prescriptive analytics. It is a subset of predictive analytics. That means that recommendation system, which is a type of predictive analytics, is a subset of predictive analytics. And it helps prescribe or recommend an action to end users. It helps recommend data to end users, taking into consideration what kind of data you have. It helps drive decision-based ideas on your data. Now, what are recommender systems? Recommender systems is, to say it in a single line, it helps match users with items. But it can be done in many ways. You can take, the very basic form is basic form of recommendation system is search. So when a user comes in and searches, it's a kind of recommendation, you can say, but it's very static. I mean, it is not like whether it will give you futuristic predictions. It will just give you whatever you have searched for then. But the recommender systems, we'll see going forward, there are many different types, and different types is used with different motivation and for different users based on the kind of data you have available, based on the kind of question you want to ask out of the system. We will try and develop some with PubMed documents. So why do we need recommendation? As data is becoming more and more big, it's becoming overwhelming for anybody to have a context in whatever they are searching for. So if you're looking for a topic related thing, it's very difficult. It's becoming more and more hard for the search engines to predict something based on your topic, based on your context. So that's why recommendation systems are becoming more and more essential nowadays with the emerge of more and more big data. So the type of recommender systems, there are mainly or broadly 3 types of recommendation systems that we see. One is like the knowledge-based, where you actually try to engineer the knowledge, bootstrap the knowledge, whatever you have available, and try to do a static recommendation. But as I explained, it's the search. But it comes with some pros and cons. I mean, the con is basically it's static. And the pro is it does not have a cold start problem. So let me describe the cold start problem with respect to recommendation systems here. When a new user comes in or a new item comes into your corpus, I'm taking just a document data set for the ease of understanding. When a new document comes into your corpus, it's very hard to have any idea about that document and predict based on that document. So you have to build up a user profile or an item profile before you can start predicting on the trend of that item, how similar they are to the existing items, or what interest the user have for who is searching for items. So take a very typical example of Netflix. If somebody is only searching for animation-related movies and suddenly they start searching for action genre movies, it's very difficult to predict how they would rate action genre movie, because the user do not have a profile based on action genre movies. The user only have profile based on animated movies. So that kind of like a pre-processing or pre-data is required for the recommendation systems to start. Not having that data is called a cold start problem. So as we can see, knowledge base, because it's static, it does not require a cold start. It does not go under cold start problem. Any new user can come in and search for whatever item is present. No previous user profile history is required. For content-based recommendation, we can, as I explained, we can understand that it has the cold start problem for new users. But the pros is comparison between the items which is present is very easily possible based on the content. So if your data is elaborate enough, if it supports enough information, then comparison between items can be easily done using content-based recommendation. Content-based recommendation can also be context-dependent. So if you go in and search for documents, so document searching is mostly content-based, but you try to capture the context of your search. So suppose you're searching for one type of DNA. So it should be known whether you're interested in a human DNA or a mouse DNA. So if you just search for DNA, random data will be coming up. So that you need to, based on the user profile, we can understand what kind of DNA the user is interested in, whether he or she is working with human DNA or mouse DNA. So that's the catching of the context of the content. That's what we call context of the content. It gives you more relevant recommendations. The most widely used type of recommendation is the collaborative filtering technique. It gives you it has cold start problem for new users and new items. However, it gives you very innovative and very accurate recommendations. We'll see how it works. So a commonly used example of user-based collaborative filtering is we take this data, a small data, and we try to predict new books to customer C, who is highlighted there. So we see that customer C has bought book 2 and 3, and customer B is very similar in content and context to customer C, in the sense that they also have bought book 2 and 3. Customer D is also related, very closely related, but he or she has bought only book 2, not 3. So we apply weights based on the closeness. There are ways to measure this kind of similarity. We'll go into it. But yes, based on the similarity, we weight that customer B is more closer, higher in ranking in closeness to customer C than customer B. So book 5, which is searched by customer B, would be more highly recommended than book 6, which customer D had actually searched for. So book 5 will be more highly recommended to book C than book 6. As you can see, A and B have no overlapping results, so their weights will be really small. It would not be taken into consideration compared to B and D. Okay, next, a new kind of recommendation systems. It is also widely used. It's called hybrid recommendation system. So you can, as I showed you, three different kinds of data here. Yes, 3 different kinds of recommendation technique here. You can combine any 2 of this technique, 2 or more of this technique. You can combine 2, 3. You can combine them, and it will give you a hybrid recommender systems. As we can see here, you can capture the user information. You can capture the content, which is the product features. You can also mine knowledge based on search and combine them together to give you a recommendation. So why do we need hybrid models for recommending PubMed documents? Would existing one would not do? As I said, when users go into PubMed, I do not know if you are aware with PubMed. PubMed is medical data, articles corpus. Its abstracts are readily usable. For our experiment, we have used only, it's licensed under Medline, so but for our experiment, we have used only the full documents which are open source available. We have not used the Medline license. So as there is no option for the users, like in Netflix, users can go in and rate movies. And recommendation becomes easy based on building a user's profile on those ratings. But in case of PubMed kind of a system, it's very difficult. A user goes in, searches, and it gives you just the documents which is being searched for. They do not get to rate the document, so it becomes very difficult based on how new documents would be recommended to them. So the steps that we go ahead with for combining these recommender system for PubMed documents is we search whatever query or whatever document we are interested in. We do an information retrieval based for users based on content and context. And then we recommend context-related documents to user based on context related with the search. So there are some steps that we go over for combining. We use the vector space model, which is actually a type of an information retrieval system. We combine step 1 and 2. Step 1 is content-based filtering on PubMed documents. So we search documents with query term. We tokenize each document into a combination of unique terms. We compare the PubMed document. We convert the PubMed document to a sparse matrix of documents and terms. So the next step is we weight the query term which is coming. So we take a document, we actually tokenize it and create unique term set for each and every document. And when the query comes in, we try to compare a similarity, documents matrix similarity, how similar each and every query is to the documents they are searching for. Based on that, we assign ranks, and that's how you can say, okay, this ranking is very similar to a Netflix user rating. So we are generating the ratings or the ranking of the documents from its content. For that, we use the vector space model, as I said. I'll actually show you what vector space model is. I'll explain after this. So that was step 2 and 3. For 1 and 2, for 3, we filtered whatever. Now that our documents are weighted and ranked, we filter that using collaborative filtering technique. That is recommendation. For this purpose, we use an open source Python library called Python Rexes. It was developed by Oscar Selma, Director of Research at Pandora, and it works very accurately. So once you have your numerical data and your document ranks, all these things, information retrieved, weighted, and ranked, you can then go ahead and use a standard recommendation library. We used pandas for pre-processing of the data. We used Skikit to evaluate our model. Here we try to do 2 types of recommendation, item-based recommendation and user-based recommendation. However, I'll tell you, depending on your data, your pre-processing technique and steps would be different. I mean, I have only worked with documents. If you're working with image data, obviously your pre-processing steps to prepare your data and weight and rank your data would be different. Next, we see how IR is done through information retrieval is done through vector space model. So what do we have? We have a set of PubMed documents. We have n features. N features is the number of terms into which you divide unique terms that you tokenize your document into, describing the documents in the set. So each and every document will be divided from 0 to n terms. And whenever a term is not occurring in the matrix, it will be 0 or not a number. So, but what happens is, what happens is it actually does not work as expected. We have converted this into a sparse matrix. So working on sparse matrix is different than usually available matrix. We'll see how we work on the sparse matrix going forward. So query is also when the term after the IR, when the query comes in, it is represented as a point in the vector space. So we apply TF-IDF, term frequency inverse document frequency, to tokenized documents to weigh the documents and convert the documents to vector. We compute cosine similarity between the tokenized documents and the query term. We select the top 3 documents based on the similarity measure and recommend those 3 documents as the first step of our IR.
Quick question.
Yeah, sure.
What's the difference of the vector space versus bag of words? Is it similar?
It is very similar. It is very similar, but the vector space actually takes the content as well as the context. So it tries to compute a distance similarity based on the context of your content.
Okay, so it's one step further.
Yes, it's one step further. So these are available recommendation libraries. So each one of them works better, but depending on what kind of question or what kind of data you have. For my purpose, I chose Python Rexus. Why did I choose Python Rexus? So it is, obviously, as I was writing code in Python, it is a Python library for building recommendation engines. It works very well with SkiKit modules for collaborative filtering, content, and hybrid filtering. So it actually works very well with SkiKit. And the underlying module is KSVD, which is a generalization of the k-means. And it actually handles sparse matrix data. As I said, we have already converted, and it actually converts into a sparse matrix with only the numbers are coming in n by n features. In an n by n matrix, you get only numbers where terms are occurring, and most of the other spaces are empty. So that's how the sparse matrix is created. And it is open source. Obviously, you can go and look at the code here, as I have given you the code for Python Rexus. It is very easily installable. It's installable through easy install, pip, things like that. So it actually seamlessly integrates with your model. So now we'll move on to the code execution of the demo. We shall try to show that our hybrid model, which is a combination of the vector space model and Python Rexus, that works better than using Python Rexus library alone. So that's what the motivation is, showing that our model works better. So first we explain the collaborative filtering technique using Python Rexus library on a simple movie data set. Because I have ratings already available on movie data set. Next, we explain our hybrid model for PubMed recommendation. So we run comparative evaluations on the model, we will run root mean square error and mean absolute error. So root mean square error gives, these two actually tries to, the less the error, the more correct your model. So root mean square error gives you accuracy of your model. Mean absolute error gives you accuracy of your prediction. So lower these numbers, better is both the numbers, because those are errors. So better your model works. So we'll try to see. So the data I use for demo is a movie data format. A set is like this. We have a user ID, we have a movie ID, and the ratings. So this was downloaded from the internet. It's very easily available data set. If you search for movie data set just for your testing purposes, you'll get this kind of a format. This document, for the PubMed data set format, a lot of pre-processing is required. If you pre-process your data, like the tokenize and those kind of things, that is done through the vector space model. I've integrated into our vector space model. So when you do that, you get your data in this format. So you have a username, a unique user ID, the query term which you are searching for, the document ID, and the document rank. This document rank is the TF-IDF score, which is being scored by comparing how similar the term is to the content of your document. Then we have the document name and each doc token and combined doc tokens. I'll explain this. When you search for something like DNA, top 3 matching documents would be picked up. So each document has got unique terms, and we tokenize that document. Now we try to combine those terms and take only the union of those document terms, like 3 document terms, and do a union on them so that we get the unique combination of the terms for that search. So next time when we do a recommendation, we only take the combined document tokens so that we have a larger space for recommending more likely items. So that is used for item-to-item scoring. Before I go to conclusion, I can just go here and run the demo. So first we load the data set here, as you can see. Yes, first we load the data set here, as you can see. We import all the packages, the Rexus algorithm, which is the Python recommendation algorithm. It imports SVD. It tries to import a data, which will actually take your data into some specific format. And then we try to evaluate. Now we load our data set. I'm not running this because it will take a little bit of time, so that's why I'm not running this. I've already run this. But okay, I can start running it actually. Okay, it ran, and now I try to load the data, which is being loaded. And this is the movie data set data that I showed you. It has got a movie ID, a user ID, and the rating given by the user for that movie. So now that it has run, we tried to do, for our testing purpose, we tried to split the data set. And we take 80% as the training data set and 20% as testing data set. The next step is computing of SVD. So here I take K as 100. I could have taken less also because the movie data set which I'm considering is not that big. It's 1 million. K is actually, so now in this model we have consider K-means. It's very similar to that. So it will be 100 centroids would be considered. And now we try to compute a document similarity based on the distance from those centroids. And that's how SVD is computed here on your training data set. Once that is computed, you actually try to test how accurate your model is. And for that, we run it. And root mean square error and mean absolute error would be given. So you're calling those functions. You're trying to predict, generate a predicted rating. And now you're testing whether your predicted rating is how similar they are to your rating. So as we can see, accuracy of this model is not very good because it's coming to 0.9073, things like that. And mean absolute error is coming to 0.71, so which is also way higher. It should be less than 0.5 to be very accurate. So, I mean, way less than 0.5, but yes, it should be less than 0.5. The next step that we do compute is item-to-item similarity. So we take Toy Story and we take Bug's Life because we are only having IDs. I've given out the names from the movie data set. So we are trying to compute an SVD similarity. We see that they are similar, but it is not, the similarity should be high. Errors should be low, but the similarity should be very high. So we see that it's not very similar. It cannot, in here, it's not capturing the content of the movie in any sense, or the context of the movie in any sense. It's only doing recommendation on the user-given ratings. So that's why the similarity, it cannot capture the similarity very well. So, so the SVD similarity, when we compute here for one item, like how to get movies in my corpus, which is most similar to Toy Story, and I get something like this. So Toy Story is 1, and 0.81, which is quite high, is my most closer movie to Toy Story, and I see that is Toy Story 2. So Toy Story 2, so that is doing a good job actually in this case. So next we try to see which users should see Toy Story movie. We try to then recommend, now here we computed the similarity between the movie. Now here we are trying to recommend users for this this movie to users. So which user would be most interested in getting this document? And we see that user 869 would be most interested to actually see this movie based on the movie rating. So now we move on to, that was based on only collaborative filtering, only item and user based on ratings. So now we move on to our PubMed example and try to show how our model is working. So here, first we pre-process and load the data set. I've just given all the steps. First we pre-process and load the data sets in a database. We do information retrieval and weighing of documents using vector space model, and we save the output back to database, and then we run recommendation Rex's library on that data set, on that stored data, the already ranked data. So it works like this. It asks you the search query, and it asks you the user who is searching for that query. And then we compute SVD, as I said, using Python Rexes once it's stored in database. And then we try to compute similarity between two documents, get the similar documents. So when this is searched, the user ID is 11, user name is Rita, document ID is actually the PubMed ID, and we see the whole name of the document is given out. So we are trying to compute which item in the PubMed is most similar. So it's Arabidopsis DNA, which is a kind of a maze DNA, which we are working with. So it's very unique, right? It should not give you documents it should not recommend you documents which is human DNA or mouse DNA. So we see that if you search for 7866025, ID 7773017 is recommended. Let's see what these documents are. So this is 7866025, which I searched for, and it is molecular dissection of G1 from Arabidopsis. It has got DNA-related data of Arabidopsis. And this item is recommended, 7773017. This is also related to Arabidopsis, as you can see. So, it gives you, it is very closely related. It tries to see the cDNA and the RNA, and that's how we can say that our model is working pretty closely. It's not recommending human or mouse related documents. And user-based similarity, we try to find users who have previously searched for this Arabidopsis DNA kind of data, and we try to find out who they are. So we see that user 8 is very similar to user 11. And going back here in the database, we see that user 8 has actually searched for DNA. And based on that, Arabidopsis, because that is the only data that the database could find related to DNA, which was located, because this is a small sample. So other users have not searched for Arabidopsis DNA, but one user have searched for DNA. So that user's profile is actually suggested back. And based on that, these three documents is actually recommended. So 7866056 and 77. Let's go and see if that is what is recommended. And we see that those are the three documents from user 8 which are recommended. So I can run the code and show you actually. So this is the vector space model. This document calculates the document item prediction, and this one calculates the document user prediction. So if I run this vector space model, I have actually called those recommendations from my vector space model modularly, so it will be called. So let us run this and try and see. So if I'm searching for mRNA, and I'm searching for another user, say my name, it will generate data saying, okay, mRNA is being searched by Anu, and I'm creating a user profile for Anu, and we are trying to predict whatever document is being searched for. The top 3 documents, which are most similar to the search documents, are these 3, which I'm highlighting. Can you see the highlight? Yeah, okay. So, and as you can see, the root mean square error and the mean absolute error are pretty small here. It's not 0.91 or 0.75 as we were getting using only the collaborative filtering. So we are getting very low error. Specifically, it does very well with user recommendation, though the above 3 which I showed you is item to item recommendation. But this is when it comes to user-based similarity, like which users should be recommended documents, it does, the accuracy is much higher there. So it's 0.3 here, 0.34, 0.30. So as you can see, it's recommending very correctly in this case. Okay, so the conclusion, Python Rexes is very accurate, as we saw in the prediction of how related Toy Story 2 is to Toy Story. So it is very accurate recommendation library, and that's why we use it. So the hybrid model increased the prediction recommendation accuracy. As I showed, it actually reduces both the errors and gives you a very high accuracy. We have got a great community support for this, both VSM as well as for Python Rexes, and any Python-related library package to talk about. So that's why we chose Python to work on this. And we actually, the cons are parallelization is not that great. So when we took this model to work in using PySpark MLlib in our supercomputer, the accuracy reduces actually. It does not do that well. I think it's mostly because we have to install, if you're using a modular kind of a Python, you have to install it in different nodes, and that reduces the accuracy. For big data, we need to use different functions instead of SVD. SVD doesn't do very good on like huge data sets. If you have like petabytes of documents, it would not be able to compute very easily, because then you have to choose a K, and there being many documents, many non-related documents would also be given similar distances, and they would all be clustered together. So SVD do not perform very well on big data. There is something called SVD-lib, which actually works very well with big data. So acknowledgements, I've used these previous users' works, and from that, the motivation is derived. And that was my talk. Thank you. Do you have any questions?